In this lecture, we'll discuss the fast Fourier transform and the concept of aliasing. Till now, we have seen that the discrete Fourier transform, or DFT, is defined by this equation, that is, knowing the values of a function in time domain or the spatial domain at n points, we can get an equivalent set of coefficients denoted by capital Fn. Also, once we know the DFT, we can perform this operation over here, which is called the inverse DFT, and we can recover our original signal in time domain. And we've seen that this equation to compute DFT can be written as multiplication of this n cross n matrix with an n cross 1 vector of the values of the function at discrete times. Although this approach of matrix multiplication looks straightforward, it involves large number of operations. So because we have an n cross n matrix and we are multiplying it with n cross 1 matrix, that means this matrix multiplication, or to compute the DFT, requires order n squared operations, and here we'll account only for the multiplication operation because that is the slowest in computation. So what we can say is that the computational cost of computing the DFT scales as order n squared, where n is the length of the discrete signal. But in practice, DFT is not computed using this matrix multiplication, and there's a highly efficient algorithm called the fast Fourier transform, which we will call as FFT. So what FFT does is that this matrix multiplication involves a lot of redundant calculations, and FFT avoids that, and it allows you to compute the same DFT in lesser number of operations. And in fact, FFT requires only order n log n operations, where log has a base of 2. So this is in contrast to order n squared operations. So note that this n log n is almost as if the number of evaluations scale linearly with n, because the log n term increases slowly as we increase n, and particularly at very high values of n, the log n term increases very slowly. So it's essentially linear with some small correction term, which is log n over here. So FFT is simply an algorithm to compute DFT, and this algorithm was developed in 1965 by James Cooley and John Tukey, although similar algorithm was known to Gauss in 1800s. So clearly, looking at the number of operations that FFT requires, FFT leads to a dramatic reduction in the number of operations and correspondingly significant speed up of computation of DFT. Note that FFT is just an algorithm to compute DFT. However, because of widespread use of FFT, it is common to hear that we had a signal and we computed its FFT, although what we do strictly is to compute DFT using the FFT algorithm. FFT in its most basic form requires samples which are powers of 2. So let's say n is power of 2, let's say 2 raised to power m. Although algorithms exist and there are ways you can compute FFT for other values of n, but let's stick to n, which are just powers of 2. To understand the speed up offered by FFT, consider that we have n equals to 1024, that is 2 raised to power 10. So let's say the continuous signal was sampled at 1024 points, and the computation of DFT using this matrix multiplication would require order n squared operations, and in this case n squared is 2 raised to power 20, which comes out to be 1048,576. So approximately a million operations. Whereas the FFT requires only n log n operations, and that means we have 2 raised to power 10 times log of 2 raised to power 10, and because we have this logarithm with base 2, this is equal to 10 times 2 raised to power 10, and that is only 10240 number of operations. That is, if you compare matrix multiplication over here with FFT, so direct multiplication of the matrix would require 1,000,000 operations, whereas FFT requires only about 10,000 operations. So that means there's a speed up of factor of 100 in this particular case. This speed up will be better and better if you have larger sample, because the factor by which FFT would speed up would be this, that is n squared over n log n, and that is n over log n to the base 2. As we keep on increasing n, let's say we take n as 2 raised to power m, so therefore this term becomes 2 raised to power m over m. That means as we increase the number of terms, we'll get better and better computational efficiency with FFT. For the same reason, various techniques such as image processing, communications, etc. have been made possible only due to FFT. So one can say that FFT is one of the most important algorithms. So in the context of experimental science, also we often encounter large values of n. For example, even if you use an accelerometer, the typical sampling frequencies that one might be using would be about 1000 hertz or 1 kilohertz. That means you take 1000 samples in 1 second, and this is very typical of data acquisition using, let's say, accelerometers. Now if you take a signal for 8 seconds, that means you will have 8000 samples. That's approximately 2 raised to power 13, which is 8192, and now you can compute this speed up offered by FFT. So we have 2 raised to power 13 over 13, and that's about 600 times. So FFT will give you the result 600 times faster than what you would get by direct matrix multiplication. Now the algorithm of FFT has been discussed widely elsewhere, and for our purpose it is sufficient to know how to compute the DFT using FFT without going into the details of the exact algorithm, which can be found elsewhere. And fortunately, FFT has been implemented in various packages such as MATLAB, NumPy, in Python, LabVIEW, and therefore let's just focus on its implementation. So let us look at MATLAB implementation of FFT, and we look at an example where we have a continuous function that is sampled at discrete times, and the continuous function is 0.6 times cosine 2 pi 100t. That means it has a frequency component of 100 hertz and sine 2 pi 150t, so it has another frequency component of 150 hertz, and those are the two frequencies in the continuous signal. So let's go over this code. So what we have to first do is to define the sampling frequency. That is the frequency at which we will be sampling the continuous signal. So of course, in this example, we know our continuous signal, but in experiments, you won't know the continuous signal, but still you have to choose the sampling frequency. And then the inverse of the sampling frequency is the sampling interval. We choose the length of the signal, and based on that, we'll get the vector of time over which this signal has been taken, and then we compute this signal with this command over here, and this f lowercase f will have the discrete values of this continuous signal at times which are spaced at an interval of 1 over the sampling frequency. And then to compute FFT, you simply need to give a command in MATLAB FFT of this discrete function f. Now, to interpret what the output of this function is, so what you need to do is that first, of course, we know that these capital F coefficients are complex valued, and for all experimental purposes, mostly we'll look at the amplitude spectrum or the power spectrum. So what we've done over here is we've taken the magnitude of F and then divided by n. Note that we've divided by a factor of n because if you look at the definition of the inverse Fourier transform, it is Fn by n is actually the amplitude of the different frequency components in the signal. What we've done next is we'll just take the frequencies corresponding to, let's say, n going from 0 to n by 2. And then what we have done is that for all coefficients Fn, for n going from 1 to n by 2 minus 1, we've multiplied by a factor of 2. And that's because we know that we have positive and negative frequencies, so the net amplitude of an individual frequency component is twice of these coefficients, but not for the DC component, that is n equals to 0, and for capital N by 2. So we've multiplied only these frequencies corresponding to small n equals to 1 to n by 2 minus 1 with a factor of 2 so that we get the right amplitude. And of course, the frequencies, the physical frequencies that we have in the signal are given by this formula over here. Then what we do is we can plot the signal in time domain using this part of the code, and we can plot frequency versus this amplitude of the DFT coefficient in the next figure. Let's look at how the DFT of this signal looks like, and we have computed this DFT using the FFT algorithm. So this is a part of signal that has been sampled at these discrete times, and if we look at the FFT along with the corrections that we have done, that is, we've multiplied the coefficients that are going from 1 to n by 2 minus 1 with a factor of 2. So what we get are two discrete peaks at frequency of 100 Hz and 150 Hz as we would expect. And now let's look at the amplitude. So the amplitude of the first peak is 0.6, and this corresponds to 100 Hz, and that is exactly the amplitude that we have in the signal. And for the frequency component of 150 Hz, we have an amplitude of 1 over here. And note that because we have taken the magnitude, we cannot distinguish whether these are sine or cosine terms, or that means we cannot distinguish between the phase of these components. So all we get is the amplitude of the individual frequency components. Next, what we do is we can add in our code that we can add some, let's say, random noise using additional function, that is the random function, let's say something like this. And then what we have is a signal with noise, because a typical signal in experiment would be accompanied with noise. And if we have such noise, and now you'll see the benefit of doing DFT or spectral analysis, that clearly we can't understand what type of frequencies this signal would have because it looks fairly random to me. And if we do the FFT, this is what we get. Again, we can clearly distinguish the peaks that are in the signal for different frequencies. So again, we have peaks at 100 and 150 Hertz, and there's also a noise over here. But these frequency components can be easily seen in the amplitude spectrum or the power spectrum because the noise is much smaller compared to the amplitude of these peaks. But clearly, identification of these frequencies would not have been possible by looking at this time domain signal. And looking at this, you can also define what we call as the signal to noise ratio. So our signal to noise ratio, one can say, is that this is the minimum amplitude of the signal that I have over here, and this is the typical amount of noise I have. So the ratio of this amplitude to a typical value of the noise amplitude is called as the signal to noise ratio. Next, let us look at an important concept called aliasing, and that is related to the rate at which we sample our continuous signal. So in the previous example of FFT implementation in MATLAB, we've seen that we've chosen a fairly high sampling frequency. Now, while conversion of a continuous or analog signal to a discrete signal, one must choose this sampling frequency or the time interval between different samples very carefully. Obviously, one can say that if we have a continuous signal and if we sample it at very small time intervals, or let's say with high sampling frequency, then we would get a discrete signal that better resembles the continuous signal. However, sampling at high rate or high frequency would mean that we would need an expensive data acquisition system and also higher memory requirements. For example, let's say you are capturing images of certain physical phenomena at very high frequency, and sooner you'll see that if you take very high frame rate or high sampling frequency, you'll have gigabytes of data, although in certain cases that might not be required where the physical phenomena evolves slowly in time. Now, a lower sampling frequency can certainly be achieved by an economical equipment. However, low sampling frequency can lead to errors. Now, to understand what kind of problem we may have if we take, let's say, low sampling frequency, let's consider a continuous signal, let's say sine 8 pi t, that is sine of 2 pi times 4t. That is, this continuous signal has a frequency of 4 Hz. So what we want to know is that what is the frequency at which I should sample this signal so that the DFT can find its true frequency. Or in other words, what is the frequency at which we should sample so that we can reconstruct the original continuous signal using the discrete signal. For example, let's say the sampling frequency, which we'll denote by Fs, is 3 Hz. Now, if we choose a low sampling frequency such as this, what can go wrong? Let's see. So what this means is that if we have a frequency of Fs, that is the sampling frequency, then we are capturing signals at times, let's say 0, 1 over Fs, 2 over Fs, because 1 over Fs is essentially the time interval between two signals. So that means we are acquiring the data, let's say at t subscript k, where tk is given by k over fs, and k goes from 0 to capital N minus 1, because we say that the signal has been discretized or signal has been sampled at n total points. So what we'll measure is signal yk, which is simply y at discrete times y of tk, and that will be equal to sine of 8 pi tk, and that is equal to sine of 8 pi k over fs, and that is the sampling frequency, which in our case is 3. So these are the samples that you're going to get. Now the problem is if you look at this discrete signal where k goes from 0 to n minus 1, can also be written as sine of 2 pi k plus 2 pi k over 3, and that is equal to sine of 2 pi k over 3, and note that k over 3 is our tk, so we can say sine of 2 pi t subscript k. So what this means is that even though our continuous signal has a true frequency of 4 Hz, but because of the fact that we have sampled our signal at 3 Hz, the discrete signal appears to be having a frequency of 1 Hz, because the discrete signal, which is sine 8 pi tk, can also be written as sine 2 pi tk. That means this has frequency of 1 Hz. In other words, if you take a discrete signal and then you try to reconstruct that signal, it will appear that the reconstructed signal will have a frequency of 1 Hz. This phenomena is called aliasing, as this 1 Hz signal is said to be an alias of the true frequency component of 4 Hz. That is, because of the fact that we've chosen a wrong sampling frequency, the 4 Hz frequency component in the signal appears to be as 1 Hz frequency component, and this is called aliasing. And aliasing is something that we all have seen. For example, let's say you have a moving wheel. In movies, you have seen that if you have a car which is moving very fast, then the wheel appears to be turning in the opposite direction, and that is also because of aliasing. One can think of this as this. So consider you have this red color spoke and the wheel is rotating in the anti-clockwise direction. Then if you want to know the true frequency or the true direction of the rotation of the wheel, then you will have to capture the snapshots of this rotating wheel such that this red color spoke comes at these locations in different frames, and then you would know that this wheel is moving in the anti-clockwise direction. However, let's say this is the first image of the rotating wheel, and in the next image the spoke appears to be here. Then in the next image the spoke appears to be here. Then what you will see actually is that the wheel is rotating in the opposite direction, but that's not the true direction of rotation or the true frequency at which the wheel is rotating, because there is an aliasing effect. To understand aliasing, there is another interesting video whose link I've shared in the description of the video below, and in that video you can see that there's a clock whose images are being taken at every 55 minutes. So clearly you can see the direction of the hour hand comes out to be correct, but the minute hand appears to be rotating in the opposite direction because we've chosen the incorrect sampling frequency. Now, coming back to our example, let's look at it in more detail. So let's plot this signal. So in this figure, you can see that we have a signal y is equal to sine 8 pi t, shown in this black line, and we sample this signal at a frequency of 3 Hz. So this is a 4 Hz signal that we are sampling at 3 Hz, and you see that we get these points shown by these blue dots over here. And now certainly these blue dots pass through the 4 Hz continuous signal, but if you look at a smallest frequency signal, continuous signal, which goes through these points, that is actually the signal of 1 Hz. So clearly, if you do the discrete Fourier transform, you'll see that you'll get a peak at 1 Hz and not at 4 Hz. So this is aliasing. So your high frequency signal would appear as a low frequency signal when you do the DFT. Now let's say we can ask, can we choose a higher sampling frequency and recover our original signal from the discrete signal? So to see that, if we choose a sampling frequency of 6 Hz, then we will have discrete signal sine of 8 pi k over 6, because the times at which signal is taken is given by k over 6, and this is equal to sine of 2 pi k minus 4 pi k over 6, and that is equal to minus sine of 4 pi k by 6, and because my discrete times are k by 6, we can say that that is equal to 4 pi tk. That means instead of having the frequency, that is the true frequency of 4 Hz, what we see is that our signal, that is the signal that has been sampled at discrete frequencies with the sampling frequency of 6 Hz, appears to be a sinusoidal signal with a frequency of 2 Hz, and that is shown in this plot over here. So again, the black curve is corresponding to sine 8 pi t, that is the 4 Hz signal, and we sample at discrete points, but the signal, you can see, appears to be that of minus sine 4 pi t. So that is even though if I choose a higher frequency of 6 Hz, still I have this aliasing effect. So what is the frequency that we must choose so that we don't have this aliasing effect? So if we take, in this particular example, that's a special example, if we take sampling frequency of 8 Hz, that is twice the frequency in the actual signal, we see that all the points that have been sampled have an amplitude of 0. That means it appears to be a signal with 0 frequency. So now let's look at what is the sampling frequency that we should choose so that we can recover the true frequency in the signal. How should I choose the sampling frequency? So the answer is straightforward. The sampling frequency should be greater than the twice of the maximum frequency component that we have in the signal. So let's say in our previous example during MATLAB demonstration of FFT, we've taken this signal which has 100 and 150 Hz components. Then if we want to get the true frequencies in this signal using discrete Fourier transform, then we should sample this signal at frequency that is greater than 2 times the maximum frequency. That is, the sampling frequency should be greater than 300 Hz. And in our example where we had the 4 Hz signal, there the sampling frequency should have been greater than 8 Hz. Note that the sampling frequency should not be chosen equal to 8 Hz, because we've seen that if we choose 8 Hz sampling frequency, what you actually get is just a DC signal. In this particular example, that is not true for any general signal. So the criteria that one should follow is that the sampling frequency should be chosen such that it is greater than 2 times the maximum frequency that one can have in the signal, and this result is called the Shannon sampling theorem. So in other words, one can say is that if you have a system by which you can sample signals at a frequency of fs, then the only meaningful frequencies that you're going to get in that discrete signal would be those having frequencies less than fs by 2, and this fs by 2 is actually called the Nyquist frequency. Now let's go back to this example over here and then see that if we choose wrong sampling frequency, what will go wrong. So again, we have a signal that is continuous signal 0.6 times cosine 2 pi 100t and sine 2 pi 150t, that is signal with 100 and 150 hertz components. And first, let's see, if we take sampling frequency of 500 hertz that we've seen previously, then clearly we can get the amplitudes correct and the frequencies that correspond to the true frequencies in the signal. And that's because my sampling frequency is greater than 300 in this case, that is twice of the highest frequency component in the signal. Now let's see what happens if we choose a sampling frequency of 350 Hz. Again, this satisfies the criteria that it is greater than twice of the maximum frequency component in the signal, and again we have the correct frequencies, that is 100 and 150 Hz. Now what we do is, let's change the sampling frequency to 270 Hz. So clearly this is less than 2 times Fmax. And now let's see what goes wrong. So we have peaks in our amplitude spectrum at 100 Hz that corresponds to this component, and that's because the sampling frequency of 270 Hz is still greater than 2 times 100 Hz. Therefore, that frequency component is correctly captured by the DFT. However, this component that is at 150 Hz now appears to be at 120 Hz, and clearly that's not correct, and that this is because of sampling at frequency of 270 Hz. Also, let's say at 120 Hz, now what we have is that we don't satisfy the criteria that the sampling frequency must be greater than 2 times the frequency of the signal that we want to capture. In this case, the sampling frequency does not satisfy this criteria for both of these frequency components. So the 100 Hz frequency component appears at 20 Hz and 150 Hz component appears to be at 30 Hz. And another way to think of this is like this. So let's say this is my amplitude spectrum. So if we choose a sampling frequency of 120 Hz, then we know that the meaningful frequencies would only be up till 60 Hz, because we know that the spectrum will fold after n by 2. And let's say my true signal had a frequency of component of 100 Hz. But what will happen is that you'll see that this gap is of 40 Hz, and what you're going to see is a frequency that is mirrored across the 60 Hz frequency. That is, you take 40 Hz gap over here, and that's why you have the 20 Hz peak over here. Similarly, if my true signal had a frequency component of 150 Hz, that is, you have this 90 Hz difference, so 90 minus 60 is 30 Hz, so you'll get another peak at 30 Hz. So that's how aliasing works. So the point to note over here is that we clearly know that our signal, in this case, because we know the continuous signal, has frequency of 100 Hz and 150 Hz. But in experiments, you would not know what are the frequencies in the actual physical phenomena that you're trying to measure. What you will actually get is just the discrete signal that has been sampled. And note that the frequency components that have been once sampled at the rate which does not satisfy this criteria would be aliased. And once you have a spectrum such as this shown over here, and you see peaks at 20 and 30 Hz, there's no way to recover the true frequency component. Or in other words, if you choose a wrong sampling frequency and you get peaks at wrong locations in your amplitude or power spectrum, there's no way to tell whether these peaks are aliases of the original frequency components, or these are the true peaks. Therefore, while sampling, one must judiciously choose the sampling rate or the sampling frequency, having in mind the estimated highest frequency that one expects in the measurement. That means you must have an idea of what would be the highest frequency in the true signal which you are going to measure, and based on that you choose your sampling frequency. Now one may ask that how can I know what frequency is going to come in the signal? In fact, this is true for any measurement. So let's say you want to measure temperature, then you must have an idea of what the typical range of temperature you are expecting to choose the appropriate thermocouple, let's say. Similarly, for making measurements to know the frequencies, you must know what would be an estimate of the frequencies in the true signal, and based on that you must choose your sampling frequency. So another way to avoid aliasing is to filter out frequencies that are greater than fs by 2 in the signal before sampling. And this is very important, that once you have sampled and you've already made an error and there's already aliasing, so before even you digitize your continuous analog signal, you must remove frequencies that are greater than fs by 2, because the only meaningful frequencies that one can get from DFT are those having frequencies less than fs by 2. So how you can do filter? So clearly you cannot use a digital filter because you need to apply this filter before sampling, and therefore you must use an analog filter. For example, in one of the previous lectures we've seen that this RC circuit acts as a filter, and it acts as a low pass filter. That means if you give a signal of u of t, then and you measure voltage across this capacitor and you get a signal of v of t, then v of t will not have high frequency components, and those will depend on the resistance and the capacitance that you choose in your circuit. In other words, you need to have some kind of a hardware filter to remove these frequencies greater than fs by 2 before you sample and digitize the continuous analog signal. So to summarize, what we've seen in this lecture is that FFT is an algorithm to implement the discrete Fourier transform DFT in a highly efficient manner, and in practice whatever DFT we compute, we do it using FFT. And we've also seen that we cannot sample the continuous signal at any frequency we want. That sampling frequency must satisfy the criteria that the sampling frequency must be greater than twice of the maximum frequency component in the true signal. Otherwise, those high frequency components might be aliased and might appear as low frequency component. And once you've made this aliasing error, you won't be able to distinguish between the true frequencies or the aliased frequency. Therefore, either you have to choose the sampling frequency judiciously, having an idea that there's no high frequency components having frequency greater than fs by 2 in your signal. Otherwise, if there are high frequency components in your signal, then you need to use some analog filter to remove all frequencies having frequencies greater than fs by 2 before you perform sampling of the continuous signal to get a discrete signal.